a normalizable state. It is always not quite normalizable, at least in unitary theories, and that's easy to show. It is, however, almost normalizable in the sense that the infinitesimally regulated state, e to the minus epsilon h times beta, where again this is the circle Hamiltonian, is always normalizable for arbitrarily small positive epsilon. So in the presence of a boundary, causality, energy conservation, and conformal invariance imply that the left and right moving stress tensors at the boundary are equal. Now at finite temperature beta, we can Fourier transform along the thermal circle and exchange the roles, again, that should be an of, Euclidean time and space. So since we're Fourier transforming a boundary condition in the integral channel, this translates in the circle channel into a statement that certain linear combinations of Fourier modes of the stress tensor annihilate the boundary state B. But Fourier modes of the stress tensor on the circle are just Virasoro generators. So the form of the equation is L sub n minus L tilde sub negative n on B is equal to 0 for all integers, positive and negative. So these are the usual Virasoro generators, left and right. And this really just comes from the Fourier transform of that. And this is, people call actually different things the Carty condition, but this is sort of one of the Carty conditions. Now, but given this condition, it's very straightforward to show that C left is equal to C right. It's just, you just use the Virasoro algebra, and I didn't even put it on the slides. It's a homework exercise. But basically, take this equation, multiply on the left by the same equation with the ends flipped in sign, and then just subtract that from the opposite order, and you get this. So there's no such thing as a boundary condition for a two-dimensional CFT with unequal central charges. Any boundary state has to vanish, which means in the interval channel that the Hilbert space is on the interval is just empty. There are no states in it. So, and physically, there are all sorts of other ways to see it. It's easiest to see maybe with C right just equal to 0. So in Euclidean space-time, on the Euclidean cylinder, you can see that any meromorphic function on the cylinder that vanishes on the boundary, obviously it's to vanish identically everywhere. It's just a standard complex analysis. So the two-point function of the left-moving stress tensor has to vanish because it's meromorphic and it vanishes on the boundary. But that means that C sub left has to vanish as well, because C sub left is the coefficient of the double pole in the two-point function of the left-moving stress tensor. Simple enough. So we've shown that a conformal boundary condition implies C left is equal to C right. There are ways of understanding it in Lorentzian signature as well. For instance, go to the half line, throw a state of energy E, or throw a full complete set of states of energy E at the boundary, and it has to reflect into some other set of states. But if the two central charges are unequal, then Carty's formula says that the asymptotic dimensions of the Hilbert space at those energies are also unequal. So there's no invertible linear transformation that works for both a left hand and a right hand boundary.
What about 3D theories that have a 2D boundary?
The 3D is completely different. But what you mean, like
with a 2D boundary, so it has could it have a chiral CFT on a 2D boundary?
Yeah, that's fine.
But then I say, well, look, there's a gravitational anomaly. Right. That just tells me that there's some kind of anomaly inflow.
Right. But no, but you can't make a boundary of that boundary. Try cutting that three-dimensional bulk in half. You won't make a boundary of the two-dimensional. You won't make a two-dimensional edge theory with boundary. You'll just create a second component, right? So you'll do this.
But it's not a purely 2D system, though. How do you understand?
So here is your gapped material with an edge, and so now I'm going to try to create a boundary. I'm going to do that. I'm going to cut it in half. Boom. But it doesn't create a 2D theory with boundary. It just creates two 2D theories without boundary. You just have two sets of chiral edge modes. One circulates along this side, the other circulates along this side. But the two-dimensional theory doesn't have a boundary. you know, the yellow thing is the edge of the material of the topological superconductor or whatever it is. The pink thing is all the massive Majorana fermions that live in the bulk, and try to create a boundary. Well, you can't. Just cut it in half, boom, split it in half, but you just create, another boundary component. Now you just have two chunks of material made of massive Majorana fermions. Each chunk has its own set of power electrons. So you don't get a 2D theory with boundary that way. You get two 2D theories without them.
What happens if the space-time is not compact from the beginning, like R3 and cut into 2 and carry R2, and we can still have a
Well, but you still don't create a boundary for the two-dimensional system. You just create a system with a corner, but not a boundary. So you mean like this?
Yeah.
In the rear. Yeah, okay, but try to create a boundary. So I'm going to cut it right here. I just cut that. But it just does this.
Okay, let me put it this way. Are you saying there's no such thing as heterotic M theory?
What?
We have gauginos on the boundary.
It's an 11-dimensional theory.
It's a 10-dimensional boundary.
Yeah, but
That's even dimensions. And I can go down. I can talk about a 5D theory with a 4D.
we're talking about two-dimensional.
No, my question was: suppose that it's a 2D boundary and there's some 3D thing in the bulk.
Right. That's exactly what I'm talking
You're
about.
saying there's no such thing as chiral stuff?
No, I don't think I made any statement like that. I think I'm talking specifically about two dimensions with a three-dimensional mass.
No, I'm just trying to figure out where. So, would you say that I'm not allowed to have chiral things like living on a boundary by a 5D theory with boundaries?
I don't think I said anything about any situation other than two dimensions.
Yes, I know, but I'm asking, how is this going to generalize? Or
We don't know the full generalization. So even 6 dimensions is complicated because there are multiple different anomaly coefficients. But the 2-dimensional case is really simple and straightforward. And no, Majorana fermions in the bulk certainly in chiral edge mode certainly do not give a counter. I thought that's what you were trying to say, that they gave a counter. You're shaking your head.
okay, I just don't understand what's going on. Okay,
Wait, sorry, what?
I don't understand what's going on, but okay. You keep going.
Can you be more specific?
No, I can't. Sorry.
Okay.
I think the way of bypassing is using the latest series by going to higher density.
Yeah, okay.
Do you have this problem for this case? You have the chiral boundary.
No, it's not a counterexample. You have each so if the transfer space is compact, you have both chiralities.
So how about boundaries open without
If the boundary is open, then the spectrum is continuous. And the spectrum on the surface is continuous, not discrete.
they not get this value?
That's why. Well, it's not because of a gap. It's just that the spectrum of the 2-dimensional theory on the circle is discrete. But I want to address whatever Jonathan's asking because I do not understand what it is.
But there's a general statement about what's going on in any even-dimensional CFT.
No, I'm talking about what's going on in a 2-dimensional CFT.
Okay, so nothing applies for higher dimensions. Got it.
Things happen in higher dimensions, but I'm not saying what those things are.
Okay.
Do you want me to say some random wrong statement? Yeah, I can accommodate you if you want, but it's not going to be correct.
Okay.
But the statement I can make that's definitely true is that the situation in 2 dimensions is very simple, and that has implications by dimensional oxidation for theories in higher dimensions. But that's all.
Okay.
So together with the Green connection hypothesis and the implication from the existence of a lattice formulation, the existence of a boundary, we can show that the existence of a lattice implies the existence of a consistent boundary condition, which implies C left is equal to C right. So we've proven the generalized Nielsen-Anomaly theorem.
Where did you use the hypothesis?
Which hypothesis?
This Friedan.
Because I had to be sure that the boundary theory would flow to a conformal boundary theory, so I could use the Carty condition. So it may be possible to bypass it. So there's a kind of deformed Carty condition for non-conformal theories that L sub n minus L tilde sub n equals the Fourier mode of some relevant or irrelevant local operator. And we sort of tried to prove it directly there. Maybe it can be done, but it got kind of complicated. Okay, so the result is powerful in its own right, but it's closely related to quantum information theoretic ideas as well. So we observed earlier, the tensor factorization of the Hilbert space is manifest if a lattice regulator exists. Okay, so we have this. So the existence of a lattice regulator implies the existence of a consistent boundary condition, which implies that C left is equal to C right. The existence of a lattice also implies the existence of a tensor factorization. We'd like to fit these conditions together into a single sequence of logical implications. So we'd like to try to derive the existence of a boundary condition from the existence of a tensor factorization, so that we can say this. If we can show that the tensor factorization generates a boundary condition of some kind, then we can show this whole sequence, and it turns out to be true. So let's establish the middle length. Let's see how this works.
So, I want to argue that you can have a factorization from lattice.
Well, just because you take the Hilbert space of all the sites on the left and the Hilbert space of all the sites on the right, and that's it. That's the full Hilbert space.
But in your case, it's not a lattice landscape theory.
So again, I'm ignoring short distance issues, but I can make that more
So
precise.
it's like a scale theory.
It doesn't matter what kind of field it is. All I'm saying is modulo short distance degrees of freedom near the entangling surface, which that's really an orthogonal issue that I didn't want to go too deeply into. But modulo that, right? The Hilbert space really tensor factorizes into those two halves. So the reason I can mod out by that, so the more precise statement, is that even in a gauge theory, the Hilbert space in region A, the full Hilbert space on the spatial slice is this. It's the tensor product of the Hilbert space in the left half and the Hilbert space in the right half, and the Hilbert space of some set of degrees of freedom at the boundary, modulo some gauge group that acts only on degrees of freedom in the neighborhood of the boundary. Right.
I think in this case, they change the Hilbert space.
Yeah, they do, but they only change it at short distance near the entangling surface. So that's what I mean when I say modulo short distance stuff near the
I
entangling
think you want to say that you can modify Hilbert space to do Taylor iteration.
I'm saying that this is an exact statement that applies even in gauge theories.
I think that this likely is the model user representation to extend Hilbert space. They use representation to factorize the Hilbert space.
Yeah.
Yeah. So in this case, they modify the Hilbert space, extend the Hilbert space. So it's not original Hilbert space.
It's not, but it's the difference between the original Hilbert space and the right. So the difference between this is the exact full Hilbert space. So the difference between that and this part is just short distance degrees of freedom near the entangling surface, and mining out by gauge symmetries that only act in the neighborhood of the entangling surface. So the only difference is some short distance gauge symmetries. So in other words, it's just putting in some short distance matter and some boundary matter and boundary gauge symmetries. Right. So that doesn't affect any of the conclusions.
Simeon?
Yeah.
For this argument, do you really need the existence of conformal boundary, or an existence of conformal domain will also be sufficient?
I think you might be able to
The folding trick or something.
yeah, but yeah, you might be able to generalize it to like interfaces and stuff like that. I think probably you could do stuff like that. We didn't, but I think probably you can.
So it's a necessary to get the A, B, and boundary to do the product?
That's right. The tensor product of
Yeah.
A, B, and boundaries.
I guess you should use the way sum boundary condition, A to the product B. You should sum over different boundary conditions.
Yeah, you
So,
can
so it's not in the product for three slices. It's just two.
No. You don't get any generality that way. You can define a discrete label that labels your different boundary conditions and call that something that discrete label something in the matter that lives here. So it's really, this is the general of the state.
Is it no problem even if we consider some macroscopic Wilson loop operator active on this state? Yeah, because at the Wilson loop we define the trajectory which is both span A region and B region and consider such operator and act on some space.
Yeah,
It's still no problem.
Well, problem for what? I mean, it doesn't invalidate any of the state. I'm not making any statement about the entire Hilbert space is generated by local operators. I'm not making that statement. Nothing depends on that.
Because you do not define your algebra.
Sorry.
Because you do not define your algebra.
I build it on my algebra. The only thing that has to happen is that there are local operators and that they respect the tensor factorization. But they don't have to be. They don't have to generate everything. That's not an assumption. Okay, so now I'm going to establish this middle thing because I haven't done it yet. So let me tell you how you can do it. So the basic idea is as follows. So if the Hilbert space does tensor factorize into factors, again, modulo the short distance stuff, which don't worry about that. Or if you're still worried about it at the end, ask me at the end and I'll show you why it doesn't matter. Okay, so there are two independent Hilbert spaces, H sub A and H sub B, on which one can try to write individual Hamiltonians. One can try. So if each individual Hamiltonian is locally in each region the same as the Hamiltonian on sigma, then each Hamiltonian represents a CFT with boundary in the standard sense, which in the bulk is the original CFT. So in other words, so if we can write Hamiltonians on each of these tensor factors, which are locally the same as our original Hamiltonian, then we've got ourselves a CFT with boundary. So all we have to do is establish that we can in fact choose a Hamiltonian on each factor that's locally the same as the original Hamiltonian. So now, the existence of such a Hamiltonian is almost automatic if a tensor factorization exists, but let's get into the almosts a little bit because we don't want to cheat. So there are some arguments which are a little bit cheating, and let's try to avoid cheating and be as careful as we can. But let's remind ourselves what it means to have a tensor factorization. So for any operators on the individual factors, we have embeddings. So this is part of what it means to have a tensor factorization. We have embeddings, injections into the tensor product. So O sub A goes to O sub A tensor 1, O sub B goes to 1 tensor O sub B.
Usually your call is to be improvocation.
Sorry?
Improvocation. 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 Stand-up name is improvocation. It's not embedded usually.
It's not what?
It's not embedded. It's an improvocation.
Oh, amplification. I don't know the mathematical jargon, but it's at least an injection. But that's all you. That's all. Now for finite dimensional vector spaces, we also have projections going the other way, taking the trace on one side and dividing by the dimension of the vector space. So if these were all finite dimensional vector spaces, then those injections can be reversed into projections that take you back to the individual factors. So it's the algebra of operators on the full Hilbert space has two different maps to the algebras on each side, where to map to the algebra on the A side, you just take the trace over the B degrees of freedom, and vice versa. To map to the algebra on the B side, you take the trace over the A degrees of freedom, both and that inverts those injections. So we would recover the original operators in tensor factor if the Hilbert spaces were finite dimensional. Okay. But they're not, so we can't really do this. We can't divide by this dimension of the individual Hilbert spaces. So we have to work a little harder. Okay. So these are infinite dimensional. Now we could try to ultraviolet regulate the theory so that the Hilbert spaces would in fact be finite dimensional at the very beginning, so that the trace is always well defined. And it's true, if you can do that, then you're golden. But that's really cheating. You shouldn't do it that way.
So didn't you start by assuming there was a lattice?
No. I mean, I did, but that's done. I proved the Nielsen-Nenevia theorem. Now I'm proving a refinement, where you only assume a tensor factorization. You don't assume a lattice. So I'm proving a slightly stronger theorem, which is to say, starting from weaker assumptions. But I only wanted to assume tensor factorization. I don't want to assume a lattice cutoff. I think it's kind of cheating if you do it this way, which we don't want to do. Okay, so instead we can regulate the trace using the intrinsic data of the CFT itself, namely the normalized CFT Hamiltonian H, which we use to define a heat kernel, and an operator which has finite trace in both factors and approximates the Hamiltonian and is local to all orders in the high temperature expansion. So in other words, let's define this regulated Hamiltonian, where we just multiply the Hamiltonian by e to the minus epsilon h, which is the negative of the derivative of the heat kernel, and in the end we're going to take epsilon to 0. So the point is, do you think of this e to the minus epsilon h as, roughly speaking, the identity restricted to states with energies lower than 1 over epsilon? That's what the heat kernel is. So it's a cutoff on these traces, but we don't have to regulate and renormalize the theory all over again. We assume that's already been done. We can use that regularization and renormalization procedure and just cut off the trace with the intrinsic data of the CFT itself. We can also do it with a sharp cutoff on energy if we wanted. Fine. It doesn't matter. But anyway, the point is this regulated Hamiltonian has finite trace in the full Hilbert space and thus finite trace in each factor individually. It's also a local operator that approaches h as epsilon goes to 0, and even for finite epsilon, it commutes with local operators at a point onto other local operators at the same point up to exponentially small corrections in epsilon. So you can see that for any the Taylor series of the commutator of h sub epsilon with any local operator is always a local operator at the same point. It's only non-perturbatively in epsilon that you get operators that live at other points. So then we can define the single-sided Hamiltonians this way. Again, just really thinking of this thing as a regulator of the trace. So this is the regulated version of the dimension of the Hilbert space, and this is the regulated version of the trace of the Hamiltonian. So we just regulated the formulae we had in the finite dimensional case. So again, these one-sided traces are actually exponentials of the von Neumann entropies of the reduced density matrices with thermal ensemble at temperature 1 over epsilon. And they play the role of the effective dimension of these Hilbert spaces, which are accessible with energy 1 over epsilon. So for any point in the interior of A or B, the regulated one-sided Hamiltonian is equal to the unregulated Hamiltonian plus corrections, which vanish with epsilon and are local to all orders in epsilon. So I should have said the unregulated Hamiltonian density. The regulated one-sided Hamiltonian density is equal to the unregulated Hamiltonian density plus corrections suppressed by epsilon for any point in the interior. But the boundary is different. So once you're closer to the boundary than epsilon, things are different, and operators can appear with negative powers of epsilon right at the boundary itself. So in particular, the Hamiltonian contains a boundary cosmological constant scaling as epsilon to the -1, but if there are other relevant boundary operators, they can appear too. So for instance, for a free scalar, you get depending how you discretize, you get a mass, a boundary mass term, an x squared operator on the boundary that goes as epsilon to the minus 1 as well. So in general, we can't say much in detail about the epsilon goes to 0 limit of a boundary Hamiltonian, but again, we're going to appeal to this Friedan connection hypothesis. So scaling epsilon to 0 just amounts to a boundary renormalization loop flow in a CFT. And so you have to flow to a conformal point if the hypothesis is true. And it's been conjectured that it's always true. So again, under that hypothesis, we recover a conformal field theory with a conformal boundary condition as we take epsilon to 0. And by construction, the boundary condition is unitary and energy conserving. So by our previous proof, this means the left and right moving central charges must be equal. Now, so as we set out to do, we've established the following set of implications. We've established that lattice regulator implies a tensor factorization, implies a boundary, implies C left equals C right. And we've shown formally that there's no such thing as a tensor factorization of the Hilbert space into Hilbert spaces supported in complementary regions of a spatial slice if the theory is gravitationally anomalous. So now maybe a lot of you are asking, is this boring? I'm bored. I want to go home because they're just saying formal mathematical boring things and they're boring. At least that's what I would be saying if I were you. You might worry it's too formal, and that tensor factorizations in such theories really are well defined in some suitably modified sense. Maybe you just have to fiddle around a little bit with your definitions of what a factorization means, blah, 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 blah. Maybe, but I don't think so, and I'll tell you why. It does not appear to be the case, and I'm saying appear because we're still showing this in as much generalization as one can, but the non-factorization of the Hilbert space really does seem to be physical rather than formal. So, right, so, something happened to my latex, but anyway, so in particular, one cannot write down, so if one considers a chiral fermion theory, only left-moving fermions, not right-moving fermions, and then try to write down a state which is tensor factorized, which is to say a state in the Hilbert space of the full theory, which has no correlations between local operators on the left side and the right side. In a non-chiral fermion theory, it's very easy to do that. Just add a delta function supported mass term living at the origin, and take its coefficient to infinity. As the coefficient goes to infinity, correlations between the left and the right in the vacuum state of the modified Hamiltonian go to 0 as some power of the coefficient of the mass term. But no such operator is available in the chiral fermion theory, and there do not seem to be any states that we can find that have small correlations between the two sides. So I'm saying do not appear to be because we haven't expanded the ansatz to 100% generality yet. We're doing that now. But certainly all the kinds of easy to construct factorized states that exist for non-chiral fermions, no analogs of those exist for non-chiral fermions, for chiral fermions. And you can show in some amount of generality that that for instance for very generalized squeezed states, there are no such states with vanishing correlation functions between the two sides. So it should be possible to show it in complete generality, I think. But we're not done with that. So anyway, so let me conclude saying we've examined the self-consistency of the concept of quote-unquote entanglement in continuum field theory. In the gravitationally anomalous case in 2 dimensions, we've seen that the concept really is just ill-defined because the Hilbert space doesn't factorize in any way that respects locality, even at long distances. As a byproduct, we've proved a generalized version of the Nielsen-Nememiya theorem, establishing a no-go principle for lattice regulators for any gravitationally anomalous CFT, be it strongly coupled or weakly